This is on the computing side of things. One of the things that... Do we need the microphone?
No. Would you're fairly good.
Yeah, okay.
You're a loud one.
Yeah, I'm allowed now. So one of the problems that we're really concerned about in computing is tractability. So, quite simply, if you can express a computer problem in, say, a polynomial type construction and show that it becomes more complex as it merges over time, it'll obviously grow in size. Will some problems lead to a non-polynomial exponential growth in the complexity, or can we always reduce it to polynomial structure? So that's the question. So is it P or NP? So if it's P, we can get an algorithm and solve the problem in a reasonable time. If it's NP, then the problem becomes intractable, because it's too complex, and any solution can't be constructed faster than the complexity increases. Of course, you get complexity at a level, we know that, we're very familiar with that. But is there a golden ticket decision function which will map the exponential complexity back onto a polynomial structure? Can we do that? Deutsch's, the Turing principle in the universal quantum computer is one of the reasons why this search has been created. One of the things that I did with a colleague of mine, Bernard Dyers, was produce what we call the universal computational rewrite system. And that there was the basis for wasn't the basis for the work it did in physics, but it then provided a retrospective basis for it. Having done the work in physics, was able to provide a retrospective basis for it. And then, so to show how it could lead to physics, chemistry, biology, aspects of those things in terms of real-world 3D architectures. So the idea is to be able to describe standard model, chemical valence, periodic table, all that sort of thing, DNA, RNA, as experimentally validated, and therefore a consequence of this rewrite structure. And if one could do it in terms of this rewrite structure, then maybe one could get to the stage where one could decide whether the computer problems were tractable. And even to go as far as the human organism, the nervous system, the brain, natural language, as possibly emergent from the universal computational rewrite language itself. Well, what we did was use complex commutative, anti-commutative algebras, topological mathematical operators and so on, as well as number. So we could provide a computational rewrite explanation of human intelligence, and we wrote some papers on that sort of thing. So human intelligence and semantic natural language which are the means by which we can understand the world, we felt possibly going to be emergent from this. One of the things that is important is that we have Lie groups, germs or commutators as a general mathematical form of the concept of the derivative used in calculus, and Lou was showing that yesterday about that kind of thing. The process is described in 0 to infinity. The process by which this rewrite structure was created, that's in 0 to infinity and in other publications. And there are also some contributions are made with both Peter Marcer and Vanessa Hill incorporated into the book. And Peter Marcer and I wrote a paper, How Intelligence Evolved, showing how it could lead to a pathway on brain function and human intelligence. So if we go back to standard computer language, computer programs are written in a rewrite language. That is, you can do them in a particular way. You can write any digital computer program in a particular way with particular functions in that you can identify. There's always a finite alphabet of semantic rewrite productions. And this is, of course, the hardware interprets that and produces a finite grammar. So you can create your algorithms. But what the universal computational rewrite system did was take that idea but extend it to an infinite alphabet, in which would generate itself. So you get a description of normalized universal quantum physics field theories, and it would be self-organizing, and it would self-derive from this alphabet. And it would also describe things in terms of the fundamental conservation of energy equation from Einstein's theory, which is, of course, that one. And the fact that one could do this and produce a single operator, which was a nilpotent operator, it's squared to zero, independent of any coordinate system, gauge invariant, and in that format. We've talked about this several times in this conference. So each root squares to zero, so all the unique solutions are nilpotent. They're self-similar, fractal dimension 2, and constitute the universal fractal attractor, something like this sort of thing. So the graph of the canonical equation of Kane is showing this universal fractal attractor of dimension 2. And the Pauli exclusion principle for fermions would be the way in which this would work. The infinite alpha will produce canonical labeling. Now this sounds as though it's only quantum mechanics, but the idea is that this sort of methodology applies everywhere. And I was doing some work showing that it applied in a biological area in one of the early presentations. And we've heard a bit about Devois' ideas of incursion and hyperincursion. And one can incorporate those into this structure. I'll carry on from that. Let me just say something about this rewrite structure. I didn't really want to talk about this too much, but I don't think I can just talk in general terms as though everybody knows it. So I've got to give some idea of how it works. This is a conventional rewrite structure. It has an alphabet, rewrite rules, in other words, rules of production rules saying how things happen, a start axiom and a stopping criterion. Quite a simple structure. But all computer programming can be shown to be of that kind. This is a simple example. If we have an alphabet with two objects, A and B, yeah, and we've got two production rules, A goes to B, B goes to AB. Okay, and we start with A, that's our starting. These are the steps, and this is going to carry on. You don't have to have all those criteria. You can say let's just stop when we feel like. We don't have to have a definite stop, for example. And we haven't on this example. We start with A, and then that goes to B. So B goes to AB. Now A goes to B, and B goes to AB. You see, B goes to AB, A goes to B, B goes to AB, and so on. And eventually we generate Fibonacci numbers. So that's a way, in fact, we can generate Fibonacci numbers using a standard production system. So that's standard computer structure. Now, if we had a system in which all four elements, alphabet, start object, rules, and stopping criteria, could be varied, and they varied themselves as they went along, they rewrote themselves, then we would have a universal and self-generating rewrite structure. And the way we can do this is by assuming that the universe, or any alphabet which it contains, is always a zero totality state. No unique description. So it's zero totality. I think there was a question, where does infinity come into it? Well, the infinity is that there's an infinity of zero totality states. It's infinitely degenerate, it just keeps regenerating itself. So we have to continually regenerate the alphabet in such a way it's always new, and there's no limit or stopping criteria.
Well, what's the definition you use for degenerate?
It means that each one is zero totality, but there's always another one that's different, but it's zero totality. But that's what I mean by degenerate.
They're not all the same. Degenerate.
The degenerate is the zero totality aspect, is the degeneracy. So they've all got that one property, just as a degenerate system in quantum mechanics all have the same energy. So they've all got this zero totality, and that's what I mean. I mean, there is an infinite number of ways of doing it, just as there might be 5 ways of getting the same energy in a quantum mechanical system, that sort of thing. It's a kind of zero attractor, if you like. Sorry. We have to continually regenerate the alphabet, so it's always new, but we always have to show that it's not unique, that the one we've got isn't the unique one. There's another one, there's another one, there's another one, and so on forever. It's a zero attractor if you want. So a non-zero deviation will always produce an automatic mechanism for recovering the zero. Let's call it the conjugate. And Sabar was saying about duality always being needed at the fundamental level, and here we've got duality always at the fundamental level because we always have to conjugate whatever we have. It's always got to be zero. But this won't be unique. It always leads to a new structure. So how do we ensure that it's new? Well, we can ensure it's new if we always incorporate the previous alphabet within it. So if we incorporate the previous alphabet, the new one must be new. If we just change to a new one, then we don't know it's new. But if we incorporate the old one as a part of it, then it's got to be new, because it's no longer the same as the old one. We can compare it with the old one by incorporating it. So it becomes a sub-alphabet, if you like, and it continues indefinitely. So in other words, what we're defining is a series of cardinalities, a new cardinality all the time. But it's not a cardinality of infinities, it's a cardinality of zeros. So every alphabet will absorb the previous one in the sequence, so creating a new cardinality. So it's like a reversal of Cantor's type of cardinality, but it's zeros and not infinities. So we know it must be new if it incorporates the old one. There's lots of ways of representing this, but I'm just going to discuss one. Some sort of concatenation or placing together with no algebraic significance of any given alphabet with respect to either its components or subalphabets or itself. If it's defined to be a cardinality, then anything other than itself must be a subalphabet, because it can't be cardinal if there's something excluded from it. It's only cardinal if it includes it all. And so if one looks at it, if one looks at the cardinality in relation to some part of it, subalphabet, then the concatenation won't produce anything new. It'll still be the same old cardinality, the same old alphabet. Only if you concatenate it with itself will you produce a new one. So that's the mechanism. You look at itself with its components and it doesn't produce anything new. You look at itself with itself entirely and you have to produce something new. So that's the compulsion to the next one. So it's very convenient to represent these aspects by symbols, creating which every alphabet produces a new one, which incorporates itself as a component. That's a create symbol, that's a conserve symbol, means nothing new is created by concatenating the sub-alphabet. So essentially, if you take something within it, because it's a cardinality, it won't produce anything new. If you take the whole thing, then it has to produce something new, because it's not unique, it's infinitely degenerate. That doesn't have to be the only way of doing it, that is a way of doing it. So it's just a representation, that's all. So I'm going to start with something like that. It's an already bifurcated state, an already dualistic. It doesn't have to be the beginning, it doesn't have to be the beginning, it's a beginning. So we just start with a beginning. And we can assume it's already started from the previous alphabet, which we can't directly access. We're just starting from a point where we can start. So this is a kind of doubling process, but we don't want to think yet of the number 2 as existing. Yeah, so we can assume that previously was some 0 totality alphabet, but we've got no access to it. So we've got an ontology that exists before our observation process begins. So we can assume that. We just assume that we're starting from wherever we can start. So this is quite simple now. If I take the complete alphabet and concatenate it with a sub-alphabet like so, I won't get anything new in the sense that the total will be always the old one. However, I've got to distinguish those, so I distinguish them by changing the order of the terms like that. But that is equivalent to that, so there's nothing new. So we can generate rules for doing that if we do that. Then we've got to show that this isn't unique. So we've got to concatenate it with itself, produce a new 0 totality. So what should we do? Well, let's try putting something like this in. So we keep that because we've got to incorporate that, but we produce some new terms like those. but not define them. If the terms are undefined, we can't just have that, we've got to incorporate that as well to show that that is not the same as that. So if I do that, the new creation, by doing the whole alphabet, then let's suppose I get something like that. So now I'm going to apply the old conserve operation to check there's nothing new. So I go through all this, change the order of these things, and in the end produce nothing new. Yeah, the total's the same, and we soon realised that these can only be different. These can only be different. These parts can only be different if we apply these rules. If we don't apply these rules, then they won't be different. If we have the same rules for R and A star and R star, then R and A will be the same. We won't produce anything new. So we can do it if we do it that way, because as you can see, there's a new order developed there. So these are not the same as those. Duality is intrinsic to the process, where we're going from, we kind of, this is the concatenation, the creation of the complete alphabet with a new alphabet with a new duality in it. So it's a kind of doubling or bifurcation, if you like. We could write it this way, and almost like transforming the second one of these into this. Let's see how far we can get doing this kind of thing. Let's try the next alphabet. So we got this alphabet, we want to extend this alphabet. Let's try that. It fails, as we soon find out, because we can't avoid getting these concatenated terms involved. So we've got to include those in advance. In other words, we've got to try something like that. That's no good, because we end up with not enough terms. So let's try now doing the sub-alphabet on it to see if we get a new cycling, but we've got nothing new in the totality. And those all work very well, there's no problem. The first 6 concatenations are quite straightforward. When we come to the last 2, then we end up with a choice. We've got to either do that or that to make it work, to make it consistent. And that would be a commutative method, and that would be an anti-commutative method. In fact, there isn't any choice, because if we choose the commutative method, then we can't distinguish A and B from R. We can't distinguish A from B. We've got to choose the anti-commutative option to produce something new. The labels alone, A and B, can't distinguish the terms from each other. They can only be distinguished by distinguishable outcomes. So we have to do this. That's the only one that works within the system. And we can't do that again with C and D because an inconsistency will always reveal itself. But what we can do is create new commutative terms. So these are commutative terms, anti-commutative terms. A and B are anti-commutative. C and D can't be anti-commutative with A and B. It won't work. But we can make C and D anti-commutative with each other, and E and F anti-commutative, and we can do that to infinity. And so now we can actually produce our alphabet. What we do is have an infinite cycle of anti-commutative terms, a cycle one after another. All the terms then have a unique identity because they have a unique partner. So the partnership tells them that they have a uniqueness. And so we have a series of identically structured closed anti-commutative cycles, each of which commutes with all the others. But it's the only way we can do it. It doesn't work any other way. And if you like, it's the same structure as we produce each closed cycle. It's exactly the same structure as producing new units of binary numbers, 1, 1, 1, 1, 1, 1, 1, to infinity. So we can regard the closed cycle as an infinite ordinal sequence, and to establish this time, we got the number 1 and the binary symbol 1 of classical Boolean logic, and the alphabet structuring themselves as a series of binary digits. So in this way of looking at it, We generate a mathematics and a digital logic as properties of a process which is prior to it, which doesn't have any specific starting point, reconstructed endlessly in a fractal manner, and with self-similarity at all stages and a zero attractor. So that's what we have constructed with this. Now, of course, we can do very many representations of it, and one of them is the mathematical one, and we can have a discrete integer system which we've effectively created, and we can then apply it to the original terms and then generate an arithmetic and an algebra. The rest of the constructible numbers follow automatically. We can show that. And we can also apply the constructed number systems to the undefined state with which the process began, suggesting that the state that we started with wasn't discrete. And so we can interpret that in terms of a continuity of real numbers because it's not discrete. We can show this, the iterative process in symbolic form in that way. And these would be the successive alphabets. And of course, we can then use an algebraic representation, and again it's only representation, and this is what the algebraic representation would look like. And you can see very much that we're generating something close to a Clifford algebra from this. We can also represent these as real objects, so we can generate energies and masses and time and charge and space and things like that. So we got successive quaternion units, each of which is committed to all the others, the condition for a Clifford algebra. By the fourth stage we have repetition, and then we do that indefinitely. And we can, there's various things one can do with that. I don't want to go into the details of that because that's not what the main purpose of the talk is. So if you've got incomplete quaternion units, that's equivalent to complex numbers. So also we can see the process of the creation of zero as one of conjugation followed by repeated cycles of complexification and dimensionalization. You see that's conjugation there, that's complexification, that's dimensionalization because you've got I and J, and necessarily therefore K. And this is another complexification, this is another dimensionalization, another complexification, repeated cycles forever. And of course, because you want to do zero, if you introduce the concept of nilpotency at some stage, that's an extra constraint by which we can produce a zeroing for all the subsequent alphabets. And so we can do that as well. So we got an algebra which is isomorphic to the gamma matrix of the Dirac equations used in relativistic quantum mechanics. Okay. So the 6 alphabet threads significant, the first of which the repetitive nature, the sequence becomes established. And this is like the unit cell of the process. The word unit cell was used yesterday, and this is like that of the process. So this becomes the system rewrite order code. And this is what we've done before, physical application. I don't want to go into detail about that. This is how one generates these quantities as physical objects. They're really just abstract mathematical ones in this way of representing it, as they are in physics as well. I don't want to spend any further time on this. So, yeah, let's go back to what the meaning of the creation operation. It's always subject to the simultaneous application of the conserve proofreading operation. We saw that. The creation is always has to be checked by the conserve and proofreading. And in a sense, I said there was a duality between, not duality, but a competition between duality and anti-commutativity. And this is happening in this cycle as well. So we examine all previously existence to ensure the bringing into existence this new doesn't produce an anomaly. So we knew the new compatible, X is compatible, were different from all the X that preceded it. So this is what we do for the in this context. Yeah, this is the nilpotent condition. Each emergent fermion is non-trivially squares to zero and is irreversibly emergent, as each X differs from all that proceed from it. That's another thing. If you always incorporate the previous alphabet, it's also irreversible. because you can't go back to an earlier one, because you've always incorporated the previous one. So it's an irreversible process. It's self-similar at all scales. So I didn't say what this was about. I didn't say it was physics. I didn't say it was biology. I didn't say it was chemistry. It's about anything. It's just an information process. It means that at high levels of a higher emergent spatial geometric, the molecular chemical structure of the genetic code is, you know, and I did that in the first lecture of this session with my colleague Vanessa Hill. We got much the same things: self-similar unit elements, group symmetries, and symmetry breaking of the direct group. So this is a diagram that we drew to represent the similarity between the chemistry and the physics of this level. And you see practically everything corresponds in some way between them. And it's just because it's the same information structure, and if you like, it's based on a double space, which is the first six, which is the unit cell of this information structure. It also predicates the universal normalized quantum relativistic field theory and all these things I've said. These are semantic productions and a rewrite syntax language realized by the algebraic actions of the mathematical concept of the group, including finite, continuous, and infinitesimal Lie groups. If you look at that rewrite structure, you can derive any group you want from it. You can derive finite groups, and you can derive infinite groups. It's all based on group theory, or it is the same as group theory in effect. This ensures the finiteness of the quantum field solution of space quantum normalization. It incorporates the concept of quantum probability in the form of the complete symmetry Galois permutation group. And because you can put it in terms of the Galois permutation group, you can do virtually anything with it. Thus, the mathematical concept of group with its Lie calculus of derivatives is utterly central to the meaning of quantum physics.
9 minutes.
Okay. So the concept of a group is important because if you apply the correct syntax, you'll always get normalization or convergence, because all groups have a unit element and all elements have an inverse. The complete Galois group permutation, which realizes all these with infinitesimal elements. It's computable and determined is P, and it determines probability in quantum mechanics. So, sorry. Now, in the universe, this is very important. In the universal rewrite system, all self-organization is organized through a nilpotent structure. That's that six-fold unit cell kind of thing, in which every system has its mirror image in the rest of the universe, and so immediately generates an inverse. So if you like, the system is created in effect by reverse engineering from the rest of the universe. And so any system is like a group element with the rest of the universe as its inverse. So if you've got that object there in this infinite group, this Lie group, and that element there, the rest of the universe is its inverse.
In the talk I'm going to be giving, I think I follow this system intuitively.
Okay.
Because I use the universe to generate a process which returns the universe to the equilibrium state.
Oh.
Is that it?
Yeah, that's very much so, yeah. That would be very interesting. So the next version of the system, when any change occurs, will be another element of the Lie group. So we've got an infinite Lie group, and we just have another element of the Lie group. So the Lie system was to pack complexity into some kind of invariant. This reduces to a linear form with special constants. Now, what happens is that this whole process re-emerges at higher levels of complexity. So if you get biological viruses, they take on the geometric shapes that the DNA had before, and even galaxies, sometimes you can see in forms of double helices and so on. And we had, Peter and Marcer and I had some success in predicting the relevance of Berry phase in biological contexts. And we found that there was a possible explanation of an aspect of human cortex that way. It was mentioned in the notes to our last paper. I think I've got 40 minutes for this talk, so I should be at least okay till 10 past. Now, tractable computability requires not only that you can overcome quantum uncertainty, but that the number of computational steps is polynomial and not exponential, and also that there must be a Hamiltonian Lagrangian in the form of the Einstein equation, and that the computational space can be canonically labelled. Well, of course, you can canonically label things with fermionic nilpoints or equivalent at higher orders. So, there also this concerns measurement. So there's a fixed measurement standard unit against which measurement must take place, and I'm not going to go into all that sort of detail on this or on that. What I want to do is to go to the conclusion, I think. Yeah, I'll just mention this. All semantic rewrite turns out appertain to a single fractal universal computational tractor, and each concerns a relative geometric invariant phase, unitary one-form group, and a lead diffeomorphism. In other words, a differential exponential mapping with a differentiable inverse. A golden ticket hypothesis can be made. So you can always do a sequence of inverse logarithmic mappings to a linear simplex of constant invariance, which it would also be the case in things like the human brain and so forth. I'm going to go past all this and go to the conclusion. This is detail that you can read up afterwards. So, golden ticket tractable solution proceeds by means of a universal three-dimensional geometric dynamic computer construction or replication, and algorithmically by universal computation. It's in accord with least action and Feynman's sum of history's approach. So what we're saying here is that nature will always be structured at P at any scale because it doesn't know any other way of operating. It'll always do this. If you've got a process that always works the same way, where every time you've got a system, it self-organizes in a particular way, and a sort of alphabetic way, if you like, with respect to the rest of the universe, then this will always happen. Something equivalent to the renormalization group will always determine high-level structures. The renormalization group, you get new at each level, but it does the same function as the old thing did. If you like, it's a renormalization group. So nature will always act in such a way as to create a P, and we can disregard NP as no longer relevant. Restructuring and self-organization at all scales are forced if it's conducted by this rewrite principle. Basically, you've got a double space or space and anti-space with the total of two always being zero. So that will always organize the structure. Now, naturally, the P structures will be different at different scales. So physics, chemistry, biology, consciousness, and all those things will have different ones. And so we've got to find out what they are. We know the overall pattern creates the new P, though that creates the new P. And this will always lead to NP at the new scale because complexity always results from simplicity. But the complexity will be reduced by a new P at a high scale. And basically, we observe that in real life. We observe that we get simplicity at higher levels. Perhaps we couldn't conduct our lives if we didn't. It's almost common sense. So conditions at high scales will determine what kind of P emerges from lower ones. And this can always be expressed in terms of the methodology. And it's because of this that we can actually use the human brain sensory mechanics to make sense of the universe. We can project downwards from similar mechanism to observe ones to explain structure. This is how we can actually do science, because we can project downwards from similar structures at high scales down to lower scales. And this is the process that's happening. So the universal computational rewrite says self-organized decision process operations that result in their unique birth ordering. And so we have numerical correspondence with Turing systems of logics and all that kind of stuff, and it can be identified with physical entropy. This bifurcation really is a sort of entropy thing. As you always include the old alphabet, you're bifurcating at every point, and hence with the global irreversible second thermodynamics. It suggests that the physical cosmos, living and all these things, as fundamentally decision processing systems, are what Turing calls oracles. I've lost my place. That's it. I'll just go past that. Universal ordering go beyond those of number to operate a decision commutative and incorporate probability via the complete Galois symmetry group permutations. with the implication that quantification being unitary is topologically rather than logically driven. Okay, that's the end of the presentation.
Thank you, Dr. Marcer. That way you won't feel like you gave too many lectures.
No, thank you, yeah. Well, I think I did, but no matter.
Any questions for Peter?
Sort of thinking this over just when you were explaining it.
Yeah.
It seems like my theory of the universe is very similar to this.
Okay.
Because you're always reproducing the equilibrium state
Yeah.
from underlying processes.
Okay.
And if these underlying processes reproduce it, they're the way the system works.
Yeah, that's
That-
great.
is
Yeah,
that-
fantastic. I think that sounds.
It's a perfect example, I think, of your.
I think that sounds good, and I think that's you know the only way it can. It's almost, as I say, it's almost common sense. Because if it didn't work, then we couldn't actually make sense of the universe at all.
So if you come up with processes that don't return you to the equilibrium state,
Yeah.
you reject those.
Yeah, you reject them. Yeah. Essentially, yes.
Al?
The example that you started with in the very beginning about A, B, A, B.
Oh yes.
Would that also work with 0, 1, and 0, 1?
Yeah, you can probably do it with that.
You could probably do it.
Yeah, in fact, what you can do with
Yeah.
is quaternions in the plane ij.
Yeah.
If you can do it with quaternions. You start with A is I and B is J, and instead of going to K, you go in the plane, and effectively what you do is you push it into a bigger structure because you're forced into the plane. So you end up going in a logarithmic spiral, outwards in a logarithmic spiral. You know, your AB, if you don't allow any vertical dimension, you end up getting a bigger and bigger structure in the plane, which of course is a logarithmic spiral, which corresponds to the Fibonacci numbers.
Yeah.